Welcome to our new video on the mechanical properties of engineering materials. Today, we will discuss some fundamental mechanical properties that play a crucial role in material selection, design, and performance across various industries. Now, let's explore the essential mechanical properties that characterize the behavior of engineering materials. These properties are strength, stiffness, hardness, toughness, ductility, malleability, brittleness, elasticity, resilience, creep, and fatigue. Strength. Strength is defined as the ability of a material to resist mechanical forces without deformation or failure. Strength can be classified according to different forms of external force, including compressive strength, tensile strength, bending strength, shearing strength, rupture strength, peeling strength, shock strength, and wearing resistance. The ultimate tensile strength of a material can be found by dividing the force required to break a material by its original cross-sectional area. The unit of strength is Newton per meter square. Stiffness. Stiffness of material is the measure of a material's ability to return to its original form after being acted on by an external force. It is also known as rigidity. For an elastic body with a single degree of freedom, the stiffness is defined as stiffness equal to force on the body divided by displacement produced by the force. Stiffness is typically measured in newtons per meter. Hardness. Hardness is a metric that measures how resistant a material is to localized plastic deformation caused by mechanical indentation or abrasion. Hardness tests are fast, easy, and non-destructive. They involve applying a force to an indenter, such as a steel bowl or diamond pyramid, and measuring the size or depth of the indentation. Hardness can be measured in different ways, such as scratch hardness, indentation hardness, and rebound hardness. Hardness is dependent on ductility, elastic stiffness, plasticity, strain, strength, toughness, viscoelasticity, and viscosity. Commonly used units for hardness measurement include Brinell hardness number, Vickers hardness number, Rockwell hardness number, and Lieb hardness value. Toughness. Toughness is the ability of a material to absorb energy and plastically deform without fracturing. Toughness is the strength with which the material opposes rupture. Toughness can be determined by integrating the stress-strain curve. It is the energy of mechanical deformation per unit volume prior to fracture. The toughness of a material can be measured using a small specimen of that material. A typical testing machine uses a pendulum to deform a notched specimen of defined cross-section. The Charpy and Izod notched impact strength tests are typical ASTM tests used to determine toughness. Ductility. Ductility is a physical property of a material that describes its ability to be stretched, pulled, or drawn into a thin wire or thread without breaking. It is the measure of how much a material can be deformed or elongated under stress before it fractures. Ductile materials can be drawn into wires or hammered into thin sheets without fracture. Ductile materials are able to sustain more stress due to their ability to absorb more energy prior to failure than brittle materials. Malleability. Malleability is the physical property of a solid to bend or be hammered into another shape without breaking. If malleable, a material may be flattened into a thin sheet by hammering or rolling. Examples of malleable metals are gold, silver, aluminum, copper, etc. Brittleness. Brittleness is a material's tendency to fracture when stressed, with little to no deformation before rupture. Brittle materials have high compressive strength but low tensile strength. They also have poor resistance to impact and vibration, and poor capacity to absorb impact energy. Elasticity. Elasticity is the ability of a material to return to its original shape and size after being deformed. For example, metals return to their original shape after being deformed because their atomic lattice changes size and shape when forces are applied. As per Hooke's law, stress is directly proportional to strain. Modulus of elasticity equal to tensile or compressive stress divided by axial strain in the linear elastic region of a material. The SI unit for elasticity is the Pascal. Resilience. Resilience is the ability of a material to absorb energy when it is deformed elastically, and release that energy upon unloading. The modulus of resilience is defined as the maximum energy that can be absorbed per unit volume, without creating a permanent distortion. It can be calculated by integrating the stress-strain curve from 0 to the elastic limit. Modulus of resilience equal to area underneath the stress-strain curve up to yield equal to sigma y square by 2e or sigma y epsilon y by 2. Modulus of resilience is measured in a unit of joule per cubic meter in the SI system. Creep. Creep is the tendency of a solid material to undergo slow deformation while subject to persistent mechanical stresses. It can occur as a result of long-term exposure to high levels of stress that are still below the yield strength of the material. Fatigue. Fatigue is the initiation and propagation of cracks in a material due to cyclic loading. Once a fatigue crack has initiated, it grows a small amount with each loading cycle, typically producing striations on some parts of the fracture surface. So, thank you very much guys. If you found this video informative, be sure to subscribe to our channel for more educational content on civil engineering. Thank you for watching.